Morning, morning. Oh. Let's keep it. whilst that's warming up. Morning all. I hope you like the fact that I switch your lectures, so you don't have to traipse down the road and then back again. Is that good, is it? That's only because I noticed there was nobody in after me, and I went, what the hell are we doing going all the way up there, all the way back again? So good. So Tom said to remind you, but I guess there's an email gone out. Is it today that it actually switches? So great. Yay. Common sense prevails. Good. So don't tell me I'm not thinking of you. Right. Thank you for last week. Very intense. Loved your attention to detail. Average mark was 56%, but one group got 80. So I thought you might like to see what and why. I've got comments from all demonstrators barring one. However, I did happen to co-mark 2 sets myself. Each poster got a vote, and there were 6 votes on each poster. Okay, and I've got the marks, and I'll average them. I'm guessing that the average was 58 because overall most people got 55 to 60, and then there were a few extra that got higher. But I might be wrong, so don't hold me to that average. Sit down, young man. You're in perfect time. Which one of those 2 boxes is it? Is it that one? So I thought you might like to look at some examples of good and perhaps not so good presentation. Of course, my lovely demonstrators have half turned them around and half not turned them around, so I can't remember which one of these is the right way around. Aha. Okay. Let's pick a couple at random. Not that one, obviously.
9 and 14.
Oh, you want your own, do you?
Yes.
That's enough to show you for what I want to get across. I'll stand back in the audience, you all look up. Actually, that's not bad at this distance to be able to see. So maybe, I'm not going to criticise directly. What we've got is a positive. This was an exercise that was what's important and why is it important to a chemical engineer. Today, I've been wearing out the photocopier since 8 o'clock this morning. So I've got 4 of the groups and the 5th group on photocopying as we speak. So that you now will have 3 additional papers to match with your first paper. So most of you took your papers with you and kept them. I have got about 8 copies of each first paper left. So I'm not going to photocopy anymore because I've already photocopied 40 odd of them. So bring your paper with you. If you haven't got it, or you weren't there, then those people can get an extra copy, but I'll give you a copy for your table because you have enough work cut out to read 4 papers, 3 extra ones. You've got about an hour to do your reading and an hour to construct your poster. Okay. Last week you did a really good job. There was one group finished a bit early, and hopefully they were diligent, but hopefully they'll see why they didn't get as good as mark as they hoped for. Oops. Sorry about that. You know who I mean. You only finished 20 minutes early, so it wasn't like you finished really early. So looking at those posters, I hope you can see what's wrong with them. Okay? So straight away, what's wrong with them? Too much writing will be the first thing. Bit messy. We're not criticising them directly, but you could argue. The one on the left-hand side went with the multiple coloured options. I only had red, blue, and black pens. And the fluorescent orange came out reasonably okay on the photo, but it was almost impossible to read in front of you. So don't do that again. But you won't. I've got extra pens and I've got extra colour this time. So you might think about what was good about it now, not what's bad about it. It's a bit messy. It's a bit. Can we follow it? Do we know where we're going? We've got asterisks on this, and we've got an asterisk that's circled on this. So we've got asterisks saying the introduction and report, then it's got circled asterisks. Then we've got a little bit at the bottom that they go, oh yeah, we better put our conclusions in and we'll highlight that, which was good. So that is good to put in the conclusions. On this one, we have titles, which are obvious apart from in this one. And then we've got this paper resulted, concluded in a trade-off problem. I don't mind about the mistakes. But if there's a lot of them, it looks messy, so you mark it down. But you're doing it as you're doing it, and that's pretty damn good, I thought. What's wrong with it? I can't navigate it necessarily. So maybe a 1, 2, and a 3, and a 4 might help rather than a star, star, or a star with a circle around it. So group D9 and group 14D, good practice underlining the titles because it stands out a little bit. Okay? First attempt, I think not bad. They will probably be in the range of 55 to 60. We marked on 2 categories. We marked on what it looked like and generally ability to navigate and could it. We were not asking you to be perfect, and we didn't want the Mona Lisa or some work of art. We just wanted it to look like we could read it. Now then, the first 2 that I showed you, now these are different. These are different styles, okay? Bit obvious what's wrong with the one on the left, right? Come in, Emmanuel. No, I was 1 minute late on my own 5-minute grace myself, so don't think it. So today, you're okay to do that. Right-hand side, good practice, bad practice. Okay, so we couldn't read it at a distance, but you weren't told to read it at a distance. Was the content okay? Yes, it was. But it was too titchy, and it was hard to understand it. Now, you've got an expression in there. It says OSV. OSV decreases catalyst lifetime. 2, that poster says OSV something space velocity, but I'm guessing olefin space velocity, I don't know, is at the top, but it's not obvious. So 2 of the 5 doing this one didn't actually say what the acronym was. So we had to go, I've never seen that one before. We knew it might be space velocity, but of what? So, and that's CRE2 if you don't remember that. Well, this one looks quite nice, doesn't it? That was a no for the competition. So what we got? Extending catalyst lifetime, zeolites, paraffin alkylation, what is it? So we've taken something off the paper, we've mentioned OSV as an olefin space philosophy. Why is it important to engineers? Dum, 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 money. So, not too diverse on colour. Did their best, not a bad effort, I would have said. What do you think? You don't have to say anything. What do you think in relation to the first 2 I showed you versus the one on the left and the one on the right? Which one really impacts on you? The one on the right. What the technical content of that is, I don't know off the top of my head, so I don't know the mark for that one. But I'm automatically leaning to this one as a really good job. That's just me personally. What my demonstrators thought, and the guy who was charged with the technical input, because these are, remember, are PhD students in these particular areas. So actually you've got technical experts addressing yours, and they've done a lit review, and they've all done their first year lit review, so they've reviewed about 300 papers in their areas of speciality, and you're just looking at one. And they didn't roll around on the floor laughing, so well done to you. Okay, so congrats on that. And that's an interesting styly. But now you've got a problem in this week's exercise, because you've now got to condense 3 plus the one you had, and to try and pull out now what's important. So now I'm not changing the brief is still the same. What is important and why is it important to a chemical engineer? But take off the blinkers now, open them up a bit and say, right, I'm now designing this process, and I've got these 4 papers that I found in the literature to do my designing off. What do I need to communicate to the person reading it about the process? And then, what did I get out of those 4 papers? Now, you can imagine last year when we ran this exercise, there was tantrums to start off with in the Reynolds, well, in here actually, just around the corner, until they actually realised that I wasn't kidding and they had to do it and they get marks and it would be done in an hour and a half. And then they knuckled down and actually produced quite diverse ideas. In other words, you've seen what I mean, a simple list. The problem with the group that left a little bit early, not early, left when I said you could go, was that they condensed all their writing together, so you couldn't actually distinguish the sentences. It was really hard to read. Try not to look at the said people. But it was really hard to read what you said, so I'm reading it like this, and I've got a slight reading problem because I'm astigmatic and I'm spending time going, I'm standing further back, I'm going further. So in the end I went, oh, I can't read it, give up. And I let my demonstrator read it. and he actually was quite generous, and we voted on it as a group, and it got the mark it got. But it's got to be legible. It's got to be at least, this one is, I mean, for a first time attempt, Group A6, congratulations. Because straight away, you hit the brief. What is important? Why is it a chemical engineer? You got these 2 questions in, so you're marking straight off, and then you're reading something. Now, technically, it might have been rubbish, okay? So I don't know, but visually, it's not a bad template. Now, there's another set of photos, and I didn't want to spend too long on it, but I thought you deserved to have feedback on what you've done, because you worked so hard. I hope you don't mind. Slight indulgence, but I hope you don't mind. I'm guessing you don't, because you're not shaking your heads going, get on with it. But, there was another one I wanted to show. Probably not. It's going to be the other way around now. You watch. Oh, no, it isn't. Yeah. That was the one I wanted to show at the first one, and I clicked the wrong button. So, another idea of different styles. So now, the one at the top is interesting now, with today's exercise in mind. It wasn't voted particularly highly, but it wasn't voted lowly either. It was in the middle. What does it do? Well, it sort of tries to lead you around, and what it didn't do is what we said before. It didn't tell us where he wanted us to go and why he wanted us to go there, but it did make what is important: high demand, conversion, economic viability, and safety. You went, I'll give 1 marks for that, just for that. But it pulled together the themes, and then it radiated out like a wheel onto the spokes of the thing. The trouble is you didn't know quite what you were doing with it. Well, it doesn't take a great brain to try and figure it out. But it just gives you an idea of a different style. The use of diagrams and graphs was very rare, as you can see. You were mostly text-focused. The one at the bottom uses numbers. 1, 2, 3, 4. But the gentleman who said before too many words is right again, too many words. Now you've got 4 papers to condense into 1 poster. Same size. Maybe you use 2 coloured pens this time so you can use your highlighting. You won't get crazy with the orange one that's fluorescent, okay? Those who use that orange fluorescent marker, please do not do that again. It hurt my eyes. We finished marking, by the way, at 6:15. So just so you know, I go back to the office. I think actually we finished at 6. I got back at 6:15. Mike Porter was there letting us out. So we did mark them there and then, and we did give the feedback there and then. It's just one of my demonstrators went rogue and hasn't given me the comments. But I'll give the tables with the grouped posters that I've got comments for today, and I'll type up mine between now and the next slot, okay? Before I see it too. And then I'll leave those on the table so you can see if you remember what your poster looked like, and I'll bring the other posters with me so you can go and have a look if you really wanted to. Because you will have forgotten what happened last week, I'm sure. Okay? Any questions? Can I get on? Are we okay? Is that good feedback? Is that... By showing you everybody else's work, it gives you examples to give you ideas for today. Last year there was a step change. Okay? The first exercise to the second exercise, massive improvement. Then when you came to do the poster, it remained about the same, and some of those that did really well bottomed out and didn't do so well, and they started arguing amongst themselves and having good ideas because you've now got 4 papers to pick from, so now there's going to be an argument. I suggest you break them up so that maybe each person reads 2, and then you pull your ideas together from what you do. If you don't trust everybody, then I've photocopied 8 of everything. 40 of everything, sorry, so you've all got 1 each if you want to read all the papers, but get yourselves organised and get yourselves organised quick. Okay.
Excuse me. When we put, is it better to put graphs in there, even if it's the same as in the paper? Exactly. And if we do we put references for them? Or you're
For the sake of the poster that you did, both good questions, so everybody hear what he said? Yeah. So, 2 points. First point. Is it good to use graphs and nothing else? Well, you've got an example of where it doesn't really work. It's good. It's interesting. It was novel. It attracted my attention, and then I was disappointed with content. But it attracted my attention. It's got the big box in the middle and it's got the things around. They've reproduced it from the paper, but for the sake of our exercise, you haven't got room for reference, and hell, I gave you the papers in the first place. So I know where the information's come from. So although it now sounds like I'm asking you to plagiarise, I'm not. You can take a graph out of any literature whatsoever, as long as you do one of three things. First thing, you email the author, who's the lead author, and ask for the copyright permission. Yeah, no, that comes as a shock, doesn't it? Most people don't respond. That doesn't come as a shock. But some people do, and are quite happy to have been contacted. Bear this in mind for your design project and dissertations in fourth year. If you decide to go on a more lazy route, because you don't get a response, which is logical, you could then say, right, I've taken those diagrams, I've redrawn them, and I've modified them slightly. So then in the title you put diagram blah blah blah, modified from reference. Okay? So that gets you out of copyright and plagiarism. The third one is you do exactly what you had to do by yourselves. You redraw it completely. So when you redraw it, you probably edited some information. If you copied it exactly, I'm not bothered for our exercise, but you would probably leave something out. If you're going to the trouble of redrawing something, you might leave something out. If you've read it out, you just say redrawn and modified from reference blah. So those are the three things you must do. Obviously, I know which two you prefer. Which two do I prefer? The same two that you prefer. Okay? Do I ask for permission? Yes, I do sometimes, but not always, and it's sometimes easier when you get to my age to just say, oh, the hell with that. I can take that data and replot it in Excel and do it myself and leave one column off and say I've modified and redrawn from. And that's what I do as a standard procedure. Okay? If it makes you feel any better, in a year's time you'll be earning big bucks, or in 2 years' time you'll be earning big bucks, you'll be doing exactly the same thing. Okay? So let's not kid ourselves, but if you want to really be professional, you ask permission. Any other questions? I'm okay, I must move on now. Are we okay? Thank you all. I don't know what the voiceover on that will be like for the students in industry, but it'll be at least maybe a little insight for them if it's actually captured the recording. Has anybody tried to listen to any of the lectures? Yes, sir, you're a guinea pig, go on. No, you're not, that's not a personal slur, go on. Did you try and do it and did it work?
Yeah, it was fine.
And could you hear my dulcet tones?
Yeah.
Sometimes. What do you mean, yeah? That didn't sound too good.
No, it was good.
It's okay. I hate the sound of my voice, and you probably do too, and that's okay. Does it phase in and out as I walk around?
No, it's...
Oh, very good. Okay, thank you for the feedback. I guess you were going to say the same thing wherever the other hand was. There was another hand somewhere else. But just nod if you were going to. That makes me feel better. Thank you for that. I know, never mind. I'm not going to go into the conversation of what I sound like and what I don't sound like. Now then, I've got to find the lecture we were at last time, which was CRE Concepts. And I think we were about... here, if I remember rightly. So we've got 6... Is that where we were last time? I think it was. It was either the slide before or that slide. And we've got lots of notes written by this as well, so we've obviously got so far before he fell asleep. No, I'm just kidding. So, what are we talking about? We're talking about getting the concentration in the bulk, which for the sake of it is the bit that's in front of me, concentration in the bulk versus concentration at the surface of some catalyst. We're not talking about diffusion as we move through the pores to your individual active sites. We're not talking about that quite yet. But we automatically assume when we're doing CRE2 that the concentration in the bulk equals the concentration of the reaction, because we were talking about homogeneous systems when we were in CRE2. CRE3, we're moving now to a magic dust scenario where we've got a packed bed pretty much 2/3 of the time, if you remember what I said. A packed bed 2/3 of the time, and that packed bed then has a problem as you get across the film thickness. So I think that you're writing all that down by the look of it. Is that correct, or have you written it down already? So what have we got? We've got Kg is much, much greater than Ks. That's the surface reaction. Therefore, surface reaction controls. Why is that? Because if Ks was absolutely massive, of course, then we'd have a fast rate. So that's pretty good. We want a fast rate. Ks is much, much greater than Kg, then mass transfer controls, because the rate of the reaction, therefore, it's not getting to the actual site, so we're not getting across the bulk. So surface reaction rate is equal to that at that point. surface reaction, the actual rate of the reaction is equal to that on that step. Now that is slightly confusing, I accept, so work it through yourself. Because it's only a bit of algebra, and understanding where kg and ks come from is important. But it's not too much to worry about at this stage. So, the boundary layer. So I asked you last time, and you correctly identified that the way to reduce the film thickness or of that boundary layer is to increase the flow rate. Of course, you're limited when you increase the flow rate because your pressure drop might increase, and you don't want to have what happens when you have a backfire on an exhaust. You don't want your catalyst being fired out of your reactor because you've got too much pressure drop. That wouldn't go down too well. So now we've got the thickness, which is the delta function there, and how we're trying to get A from the bulk to the surface of the solid. Remember, we're still in the process of just getting to this. I'm only trying to get to the front row. So I'm going across, I'm trying to get across there, and if I'm faster, I start in this position, it's a lot easier. If I'm over here, it's a little bit slower. And that's all I'm talking about. Effective particle size on the fluid velocity and overall rate. So kg is a function of the hydrodynamic conditions. Fine, you'd accept that. And the fluid velocity and the diameter of the particle, so how big this is. At the moment we're talking about a surface, but if we now talk about the catalysts, which I'll bring in next time, you can see that they're either little spherical balls, or they're big tablets, or they're things with a big hole through the middle of them. Okay? So they're very different. And what you want to do is you want to get the overall rate to be as high as possible, and you've got a function which is the fluid velocity divided by the particle diameter. So the smaller that is, the bigger the fluid velocity. So you're going up that stage. External mass transfer, no longer the slowest step. So we want to work towards a situation where it just happens, and then the diffusion is the limiting step, or the reaction is a limited step. So we want to ignore mass transfer. Most of the time, engineers, you succeed in that. And that's good. And that's why most of the catalysts that you will use, you'll use a forklift truck or a JCB to put them into the actual bed. And they're usually pretty chunky things. So if you want to know the size of a typical catalyst, it can be a ball that's about 3 mil to 5 mil across, or it can be a pellet that's about half the size of your little fingernail. So it gives you an idea. Yes, sir.
Sorry, what kind of, I mean, you're saying external diffusion. What are you referring to?
You're talking about just diffusing across. So you're talking about external mass transfer, and then we're getting to the point where we're trying to get across this boundary layer. So you've got mass transport and external diffusion. You've got two things happening. You've got diffusion through the bulk, and you've got a direct film thickness to cross. Okay? There's two things happening. Your molecules are going in all directions, but they should be going straight because it should be plug flow. Okay, so they're all going in that direction. We assume simply that it's just going in that direction. It comes into contact with the surface, and we're trying to get through it. Now, in a packed bed, we're driving the flow that way. So now we're going through the audience with the flow rate. But you've still got this barrier that stops the stuff getting across to the catalyst. So we've always now got a barrier between him and me. So you've got to cross that barrier to get to the catalyst. Then we've got a diffusion. But you've got all sorts of diffusion. If you remember your flow, you'll have eddy diffusion. So things will be turning back on itself. You'll have all sorts of little currents. Okay? There are two types of diffusion, as well as one type of mass transport. But let's not overcomplicate it. Yes, sir?
Sorry, is the barrier...
Sorry, somebody coughed just as you asked the question. Sorry?
Which one is the barrier? The stuff that's flowing through before it goes into that?
The first bit said something about a barrier.
Yeah, just the barrier.
So the barrier is just simply that film thickness that you can't get across. So you can throw, if you think of it as water flowing over a substance, water over rocks, for example. Not all the water gets wet, and not all the rocks get wet. Well, they will if it's Niagara Falls, but in the case of our reactor, it's not Niagara Falls, okay? So some of it will remain dry, but the next time, a bit on this side won't get wet, but a bit on this side will get wet. So you're not getting what you expect, which is language which flows through a bed, okay? So there is a transport issue. There's a diffusion back on itself, that the water that you never get near it, but you've also got this film thickness, which you engineers know quite a bit about. Okay? But really, you've learnt instruments, and there's not a hell of a lot you can do about it, only increase the flow, decrease the flow. Increase the pressure, so you push more molecules onto the surface. That's another thing that you would do. But then you can't increase the pressure so much that you then blow the thing up. Okay?
Explain the graph again, I didn't understand.
Okay. That would appear to be all of you, yes. So, simply what you're looking at is as you change the fluid velocity, or you change the ratio of the fluid velocity of the particle size, you will end up getting to a region where external mass transfer no longer is the slowest step. Right. Let's stick with that before we go and confuse anybody. All right? So, if mass transfer is the slowest step, you're in big trouble. Why?
But they're not getting enough transfer to
You're getting nothing going to the catalyst, so you put this multi-billion pound plant in with this multi-million amount of catalyst in it, and nothing gets to the catalyst. Right? So you really want to be in this zone up here. And if you're in that zone up here, it'll reach stability, and your overall rate will be the best it can be. It won't be any better than the line because it'll flat off and it'll equal thermodynamics or be close to an equilibrium value, but it won't get any better. It'll get to what it can be. But in this way, what you're saying all the way down here, where you've got external diffusion is now the slowest step. So we're actually having mass transport issues, and we're having a problem that, well, it's just cycling around the place and it's not going to where we want it anyway. So we've lost control of our flow system, and we can't get it to the back. So I think the easiest way of understanding this graph is forget that bit and remember the top bit. And just remember what you're plotting against what. Think about if you make the particles smaller, you increase surface area. You may increase pressure drop, but you make the overall function of the fluid velocity against the particle size much bigger. And as you make it much bigger, you effectively improve mass transport. Okay? I think that should explain it. Think about it. I've got some text notes that will go with this, which I'll put up on Blackboard between the next session, so you can read them. Because those of you who are doing MSc need to be looking at Test 1. Test 1 is available until Sunday, the 18th or 19th of October. I've extended it by a week on the booklet because some of you arrive late and it's a little bit difficult when you've just arrived. So, what we're used to then, in the normal rate equation, and this whole course repeats itself so many times, I get a little bit fed up with myself saying things, so I know you'll get fed up with me saying things. Look at the equation that you see there. You've got the rate, which is actual rate now, versus the rate that we're used to thinking about. The rate is usually equal to the K times the concentration of the component that you're feeding in. R equals KCA, let's say, for the argument. So the rate is the, let's say R1. Complications arise because the surface rate reaction may be influenced by transport effects. Don't know why it did that, sorry about that. So you've got then changes now because you've now got a catalyst bed. So you've got to think about, well, how's that bed packed? This is solid fluid system. Okay, for those of you who've done the second year course. So now you've got a set of balls, all beautifully lined up in a tube. Do they all pack beautifully so there's no spaces? There must be spaces. What's voidage? So what's a typical voidage in a packed bed? Go on, I heard some numbers. Not what is it, but what might be a number for it. Are you familiar with how much space you might have in a packed bed? You've got a rule of thumb from solid fluid systems if you've done solid fluid systems.
0.3, 0.4.
I'll take somebody else's answer. Where did that come from? 0.3 is you. Okay. 0.3 to 0.4. That's a bit low, actually, 0.3. So typically, it's 0.4 to 0.6. And if you were using a rule of thumb and designing a packed bed from scratch, engineers, and you had absolutely no bloody idea how it was packed, you would say 0.5, because it's 50% space and 50% catalyst. In other words, as it's packed in, it's 50%. In this lecture theatre, it's about 50%. You go into a first year class, it's packed so tightly that they're having to sit in the staircases, so we've changed their rooms around, but it's a lot lower. It's more like 0.1 is the voidage of a packed lecture theatre of year 1 students. Okay? But year 3 students is quite spacious in here. You've got 160 bodies-ish in a space of 290. So the packing is 50%. Try and relate it to something that you see around you so you can feel it. It won't obviously be packed like this. You want a big, well, I hope it wouldn't be packed like that. Bulk density, because that's the weight of the catalyst over the unit volume of the catalyst pellets. So remember now that these pellets are not solid surfaces, they've got holes in them. So you've also got an allowance for the fact that the structure that you think is solid has now got holes in it. In the case of a zeolite catalyst, which I work with all the time, you've got 90%-ish bigger holes on the inside than the outside. So the surface area of these things is phenomenal, but also it's full of space. So actually, what's the importance of that is if your voidage you don't know properly, and you don't know your bulk density properly, you will use either too much catalyst or too little catalyst. If you use too little catalyst and you've packed it and your shutdown was every 4 years, you're fired. But hopefully somebody will advise you and there'll be technology there to stop you doing that. Okay? So specific surface area, we'll come on to that when we look at some zeolites. But typical catalyst, and this is a question in one of the tests, by the way, so those of you who are attempting the test, what's the typical specific area of a catalyst? It's usually pretty large, and it's usually above 100 meters squared per gram. 100 meters squared per gram. Think about that for a minute. 100 meters squared. So let's say for the argument the door's at 10 meters and that's 10 meters. I'm not saying it is, but let's say. So that's 100 meters squared in surface area in 1 gram. It's just worth remembering that, because you're talking about dust. You're talking about black magic dust that engineers sprinkle into the reactor because some chemist somewhere told them it'd be really good. Me, for example. So automatically put inverted commas on it and put a question mark next to it. Okay, that's just because I know. Alright? But that's what we're talking about. A gram of substance that might be no more than the volume of your thumb or your thumbnail actually has a surface area equivalent to the floor space in the lecture theatre. It's worth just bearing that in mind. So the effect of the particle size on the overall reaction. Last one with a few introductory equations, really. Now, I've picked a sphere. I don't have to pick a sphere, but I've picked a sphere. It could be a pellet, it could be a cylinder, but it's the same principle. The little wiggly lines are meant to indicate the pore structure. In this case, you have a very simple pore structure. You have a line that way, a major channel down the aisles where you get out of the room, and you've got the individual aisles with pore structure. Okay, so let's just assume that's what we're talking about in the lecture theatre, talking about pore structure. So obviously in a large pellet, a large lecture theatre where I have to get from here to there, it's going to take me longer than if I'm in a smaller lecture theatre where the door is actually where these two are sat, halfway up. So path length is really important. So if you've got diffusional constraints, in other words, you can't get your molecules to the active sites, you get a low reaction rate, you want to reduce the size of the pellet. Sounds easy, not so easily done. But that's one of the things you do. So what the graph is trying to say is exactly that. Surface reaction sequence is the slow step, internal diffusion is the slowest step as you curve round. So you want really the surface reaction to dominate your process, because otherwise why did you design a catalyst? Because if anything else dominates, it means it doesn't get to the catalyst. So you want to get rid of diffusion, you want to get rid of mass transport. You'll have it, but you want to minimize it. And then you want the diffusivity to be quick, so we get to the active site, and then we're back over here for the reaction. Okay? So for small pellets, diffusion is very quick, therefore it does not limit the reaction, so the overall rate equation is that. What's the purpose of everything I've said? Is just to make CRE2, where rate equals KCA, be the dominating force in your reactor. So that is a true representation of the rate. So you then model it. So you say, I put this amount in, I predict the rate equation is first order with respect to CA, and I say, when I put this amount in, I should get this amount of conversion. That's my model. Then you look at the real data, and you compare it, and you go, it is. Big tick. Well done. Employed. Get a promotion. However, if you've set it up, and it's a new process, or you're designing it for real in DP3, and your diffusion is massively limiting, you're getting nowhere near the conversion that you want, Therefore, the effectiveness of the catalyst is low, and therefore you need a hell of a lot more catalyst to do the same job, or you need to go back to the drawing board and redesign the catalyst. And that's the importance. Okay? So simple. I know the other graph confused, so apologies, but go back and look at it again. But simple rule is we're trying to make that the actual determining of the rate of reaction. So rate equals K, Ca, rather than a load of extra terms that are going to cause us confusion. We know we're going to need twice as much catalyst than we expect. Why? Voidage, you were going to say. You're right. So you automatically know, as a rule of thumb as an engineer, I'm going to need twice the amount that I think. Okay? And then after that, the rest is up to you as engineers and what your flow regimes are like and what your reactor looks like and how big they are and how much heat you get in and all sorts of other things that relate to engineering stuff. How turbulent is your flow, etc. Yes, sir?
Sorry, can you just repeat for the graph? You said you want to limit mass transport.
You want to minimize the effect of mass transport.
But in the previous slide you said you want the maximum mass.
Different terminology. So what I want is the maximum flow across. Okay, so I do not want mass transport to be massively affecting me. In other words, I want mass transport. No, I don't want no mass transport, if you want to put it that way. I need to get my material across, and then I need to diffuse it in, and then I need to get it for reacting.
So you need diffusion to be the quickest.
We need diffusion not to be a limiting factor. Think of it in a slightly different way. You're trying to make a yes-no tick box. Don't do that. It's a big mistake. Try to think it as I've got mass transport problems, but I want to minimize them. I've got diffusion problems. I want to minimize them. I want the rate of reaction to be my key determinant. And in 75% of all reactions, surface reaction is controlling. So in all that table that I gave you the other day, 75% of those reactions are surface limited. So that means exactly what you want as an engineer. Because what you've done to a chemist is the chemist is giving you this pristine product that he says is brilliant. You put it in your reactor, and then because you're using totally different flows on a totally different scale and everything's contacting in a totally different way, it now doesn't work. So what you do is turn around to the chemist and you say it didn't work. But it did work, but it didn't work. The question to be asking is what happened in scale-up? What is the significant difference between a small scale and my required scale? What have I done to the flow regime? What have I done to mass transport? Okay? So remember, they exist. They always exist. Just say minimize, maximize surface reaction rate. Okay? So if you're confused, go back, have a look at it again, and just think it through. I want you to think in terms of you can't make anything zero. Well, you can make the reaction rate pretty low, but that's not what you want. Okay? Sorry if I've confused. So, eggshell versus homogeneous catalyst is a little slide I would normally draw. Who's the person who managed to bring a dry white marker last week and then remember to bring it this week? You. Thank you so much. If only the staff were as good as the students, is what I say. So, what I just said, if I've got a bad catalyst, now, so the chemist is wrong and the engineers are brilliant. Okay, so we put it in, it's brilliant, everything's set up, it should work, but it didn't work. selectivity to the thing you want might be an issue. Now, in some reactions, such as dehydrogenation, where you're just stripping hydrogen off, it doesn't have to be selective. But if you're making something like paraxylene, where you've got three sorry, that's my fault. Let's say that's a benzene ring, and I'll forgive you if you don't know what it looks like. Those of you who are doing toluene disproportionation know something about this, or alkylation. Okay? Oh, the pressure of drawing on the board. This will become clearer, and I apologise for keep saying, as you get into the course, it will become more obvious. Ortho, metal. Thermodynamically, that's the favoured product. Okay, thermodynamically. So, in this case, if you made an eggshell catalyst, you would have the thing hit it, it would come out, you would get 50% and 25% of these two. Right. Who's got a water bottle in front of them? Yes, I can see them. 1, 2, 3, 4, 5. So all of you would only get a 4 times more expensive water bottle. Because the thing that you want to make PET is this thing. It's also used in clothes manufacturing, paraxylene and so on. And that's the preferred product. So if you had this catalyst, you would have 25% selectivity for that reaction, producing para, meta, and orthoxylene. So, you would then, in this case, use a homogeneous catalyst like this, where the active sites are distributed, because you'd want or hope that the chemist or somebody has told you that this catalyst is selective. It is shape selective. It will allow this thing to increase, and you will get more of it if you use a zeolite catalyst, which is homogeneous perhaps, and you'll get the 25% going to maybe 50 to 70%. Some of you doing toluene disproportionation papers and transalkylation papers today will see that in the papers that you read, because the papers are set up to try and improve the selectivity to this thing here. Now that's high-end stuff, and I know. Just leave that there for a minute. So remember, it's about rate, maximize it. It's about X, which is conversion, increase it if you can. But not in all cases, but in a heck of a lot of cases, it's the selectivity that stops you using the eggshell catalyst versus the homogeneous. If you then go, so you will know in about 6 weeks' time that this is brilliant, because we just cut the diffusional path length from all the way up there, which takes ages, to this bit. And therefore, as soon as it contacts the active site, it reacts and gives you the product. However, to get selective, you have to do fancy things with fancy catalysts. Difference between a platinum alumina catalyst or an alumina catalyst, which is cheap and cheerful, is its surface area is usually quite low, but it's cheap. A zeolite catalyst, 10,000 pounds to 100,000 pounds per ton. You've got a process that uses 50 tons a year. That's a hell of a lot of money that's going on your catalyst. So you really want to try and use something cheap. You really want to do something where you dig it out of the ground. Last thing, and then I'm finished because I've encroached on your time. I would normally have stopped at this point. Let's just look at all that. So all that introductory material was talking about minimize mass transport limitations so you get as much to the surface. Minimize diffusional constraints so you get as much through to the active site. If you do that, then the surface reaction, or your modeling reaction, your model of the reaction, I should say more appropriately, is as close as it can damn well be to a first order reaction if it's a first order reaction with respect to A, and it therefore means the rate equation equals R equals KCA is what you're really always striving to get, to the elemental reaction. So you can just put that in a spreadsheet and get that. Of course, you engineers know that that's not going to be the case most of the time, otherwise why you pay that ridiculous amount of money that you earn. It's always going to be a bit more sophisticated than that, and it's going to have other factors we've not considered yet, which is heat transfer and other such things in. But effectiveness, the general effectiveness, the rate of the reaction within the pellet, so within this baby, okay, versus the rate of reaction obtained in the whole pellet if the concentration were the concentration at the bulk, that's what CAB means, at temperature of the bulk. Okay. The rate of reaction within the pellet divided by the rate of reaction obtained if the whole pellet were at CAB and TB, temperature of the bulk and concentration of the bulk. So the effectiveness is that divided by the rate equals KCAB, let's say, at temperature. And if the thing is not 1, you got a problem. So if that ratio does not equal 1 or 100%, your catalyst is not 100% effective. Now then, what number, without prior knowledge, would you put on the effectiveness of a catalyst? Would you say it's 0? Would you say, I hope not. I just hasten to add, I'll lead the witnesses. Don't say 0. Would you expect it to be 100%? Good. So the lectures haven't been a waste to date, and I've gone a bit slowly, but it was worth the effort. Okay, because that is the basic fundamental concept of this whole course and your design project. So if you say no straight away, brilliant. Okay, I've won and I can stop labouring the point. So what would you say? Would you say it was 50% effective? Would you say it was 70% effective? What? Just generally for a general catalyst.
85.
30%.
Lots of numbers. Nobody's gone for 90, which is very good, because I've got another message across. It's unlikely to be 90. It might be 90 on a good day with a following wind. Okay, so the numbers you've said are between 30 and 80 is what we said. That's not a bad range. You would hope that I, as a chemist, would have given you a product which you could scale up, which you will have tested in your own labs at different sites at different universities probably, as well as in your own labs if you're rich and famous, like ExxonMobil and Shell maybe. Or you outsource it to certain people to do this. I do this stuff for other people all the time. You would hope to get it about 50% to 80%. So you start off by assuming, I've got an effective catalyst, it's about 80% effective. I'll